Final gather is useful for finer detail resolution, eliminating dark corners, and really nice convincing soft shadows. And this can actually be combined with global illumination for a more physically accurate solution as far as illumination is concerned. Now with final gather, rays are first cast from a light, and then one of the rays strikes an object. A series of secondary rays are diverted at random angles to calculate the light energy contribution from surrounding objects. And then this is evaluated during the render process to add the effect of this extra bounced light. So this basically what it does is it turns every object into a light source. Therefore, each object in a scene influences the color of its surroundings just as it would in real life. So I've got a scene here, it's a space jet. Now if we just go to the side view, you'll notice that there's a great big kind of dome over this. And so what this dome is it's got a white shader on it and it's got a slight incandescence value. And this is where our illumination is actually going to come from. Okay, so let's go ahead and set up our final gather. So we're going to go to the render globals. Make sure that we're using mental ray. So again, this is a feature that is unsupported by the Maya software renderer. And let's just go to quality and go to preview final gather. Okay, and then we can go into the final gather section, and you'll notice that the final gather rays are quite high. They're 1,000 by default. So I'm just going to actually turn those down a bit. Okay, so the more rays that are sent out, final gather rays that are sent out, the longer this is going to take to render. So the minimum and maximum radius, what that is going to do is control the size of the sampling region within the area which the final gather rays search for the incoming illumination information from other sources. So let's go ahead and just go back to the perspective view. Okay, and let's go ahead and do a render. Okay, so you'll notice that we've got some really nice soft shadows underneath the jet. And now the reason for that is because there are points that are being hidden from the dome shader. So it's a really nice sort of realistic type shadow. Now if we want to get any kind of color bleed, what we'll need to do is change the color of our space jet here. So we'll make it, let's make it red. And I'm just going to turn the intensity of the light. Right now it's at 0. Let's turn it to 1. And let's go ahead and do a render. Okay, so now we're getting a really nice kind of reddish tinge. So basically colored rays coming from the space jet onto our floor plane. Helps add some really nice sort of detailed, realistic, illuminated effects. The other thing is that we can change the irradiance color on the floor. So if I just go to the floor shader and just kind of scroll down here to the mental ray section, the irradiance color, basically this is going to affect or control the effect of final gather on a surface. So if we just turn this down, probably won't be as quite a reddish tinge on the floor. So it kind of controls that color bleed effect that's happening. Okay, so it's not as bright there. We'll now use final gather with a high dynamic range image as the basis of illumination for a scene. This is sometimes also known as image-based lighting. An HDR image has an extra floating point value that is used to describe the persistence of light at any given pixel. So if you look at this scene here, I've got a ring and it's on a plane and the plane is mapped with a wooden texture. But I also have, if we just go to the side view, I also have it surrounded by a sphere. And so what I'm going to do is I'm going to map this sphere with an HDR image and use that to illuminate the plane and also the ring as well. So let's go back to the perspective. And let's just map it with a regular JPEG image and see the results. So I'm going to map the ambient color with this. And I'm going to map it with the Napa Valley. Okay, and then the other thing I'm going to need to do is turn on Final Gather. So in the Render Globals, Mental Ray Render Globals, this is not a supported feature for the Maya software renderer. Just turn on Final Gather, and let's do a render. Okay, so it's somewhat illuminated, but we can get a nice sort of more realistic looking effect with the HDR image. So I'm just going to break that connection, and let's use the HDR image now. So ambient color. And HDR images tend to be quite large. This particular image is about 18 megabytes. Let's just see if we can get that. I'm getting an error message here. Okay, so let's go ahead and render that. Okay, so you can see a real sort of realistic contribution from the HDR image. Okay, it looks like it's actually in a real environment. And let's look at the comparison between the JPEG image and the HDR image. So this is the HDR image, and that's the mapped JPEG. Okay? So no lights in this scene. We're just using the HDR image to illuminate the plane and the ring. Mental Ray for Maya supports many Mental Ray standard shaders. These shaders can be assembled into shading networks using the hypershade and then assigned to objects. So if we just go to the hypershade and under the Create menu, we have our standard Maya shaders, but down here along the bottom are the Mental Ray shaders. So just a few of them. The material shader is a lot like our own material shaders. Light shaders are similar to Maya's light sources. Shadow shaders, they determine the appearance of a shadow, kind of like shadow color in Maya. Photonic materials, they determine how photons are scattered or absorbed when they hit a surface, and this is specifically for global illumination and caustics. Then we have photon volume shaders, so if you want to have volumetric caustics or something like that, then you'll need to use a volume shader, or excuse me, a photonic volume shader. Output shaders are used to post-process rendered images, things like glows, flares, blurs. Geometry shaders, they introduce new geometry procedurally at render time and so on. So there's actually quite a number of them. And then basically what you do is you hook them up into a shading network and you get some kind of a result. So let's look at one of those. Let's look at the contour shader. So I'm going to grab a file. So I've got a vase here, and I'm just going to do a regular render using the Mental Ray render. Okay, so let's go ahead and add some contours around here. So the first thing that I'm going to do is actually graph the materials on the selected object. And so you can see that we're using a Lambert shader. So now what I'm going to do is I'm going to add some contours. So just under the Create menu, under Mental Ray Materials, I'm going to use there's a lot of contour shaders, but I'm going to use the simple one. Okay, and the way that you hook this up into the network is by opening up the shading group. And under the Mental Ray section, okay, so there's a Mental Ray section in the shading group. Just middle mouse button, drag and drop that into the contour shader. Okay, and so now let's go and access some of the attributes that are on that node. So color is going to be the color of our contours, and width is going to be basically the width of the contour. Okay, now if we were to render this actually would not render contours. There's a few more things that we have to sort of add. So if we just go under the Create menu again, under Mental Ray Miscellaneous, we're going to use a contour contrast function, and we're also going to need to use, whoops, wrong Create menu there. We're going to need to use a store contrast or contour store shader as well. Now, basically, the contour store shader is going to decide what kind of information to store at an image sample location. So this will allow the contour contrast shader to decide whether two samples are different enough to place a contour between. So the contrast shader actually has a bunch of different attributes on it, as we can see here, that are further going to control the look of the contour. And then it's the store shader that's going to help kind of decide whether or not we're even going to put a contour in a certain position. So where we're going to hook these up is actually in the render globals. So let's go ahead and just go back to the render globals. Okay, and under the mental ray section, you'll notice that there's a contour section. And that's where we're going to hook up the contrast shader and the store shader. So let's go ahead and do that. So there's the contrast shader and the store shader. Now if you find that the store shader opens up the connection editor, we'll need to make a couple of connections. And the connection will be message into contour store. Okay? It might not always open for you, but in case it does, those are the two connections. And make sure too, if you are going to, if you do need to connect them via the connection editor, you might want to even just make sure that show hidden is on both sides, on the right and the left hand side. So let's go ahead and sort of further manipulate the contours by going into the contrast function. And let's just close that down. So we're going to change the Z delta and the N delta. So the Z delta is a minimum depth difference required to cause the contour, and I found that smaller numbers equal the greater chance of a thicker line. So I'm going to give this a value of 0.4. And then the N delta is the minimum angle difference between normal vectors required to cause the contour. And I found that a higher number in this instance equals a less thick line. So a thinner line, and sometimes those lines can even disappear. So I'm just going to give that a value of 12. And you can fool around with these values. You'll have to do a render and check them and then change the values, do another render. And you can actually see how those two work together. And then the minimum level and the maximum level, right now they're at 0, which means no contours. So we're going to have to put this up to 1. Okay? So there's one last thing that we're going to need to do, and that's grab an output shader. Now, output shaders are called after a regular image has been computed. So basically, it's kind of a post-process thing that we're doing here. And so in order to do that, we'll need the output shader. So there's mental ray output shaders, and we're going to use the contour composite. And just under the camera, you'll notice that there's a mental ray section as well under the camera, just under film back. And that's where we're going to middle mouse button drag and drop the output shader. Okay? So now, if we do a render, we should see some contours on our vase. Okay, so we have some nice contours. If you want to adjust the thickness, there's a couple of ways. You can go into the actual contour shader itself and change the width, or you can even go into the function level and change the Z delta or the N delta. So let's just look at that full screen. And you can see that we've got some really nice contours around the lip of the vase, as well as the outline of the entire vase itself.
Mental Ray has a handy little piece of functionality called Mental Ray Diagnostics. And this is a set of tools that is used to troubleshoot and refine render efficiency. These software renders provide visual, statistical information in the form of dots and lines, etc., that can be used for render debugging and optimizing. And this functionality is found in Render Globals in the Mental Ray tab towards the bottom, just in here under Diagnostics. There's 4 different ways that it can be used. We can use it to diagnose samples, in which case it'll be evaluating this section up here under Anti-Aliasing Quality. We can also use it to diagnose a grid based on object, world, and camera space, photon emission, and we can also use it to diagnose the BSP or binary space partition tree for those scenes that are very large where memory usage is a problem. We can use this to tune and adjust the BSP settings down here in memory and performance. So let's start off by doing a diagnose samples render. So that's going to be evaluating the min and max samples as we have up here. Right now they're set at default, -2 and 0. And let's go in here and do a software render. Okay, here's our software render. Just going to enlarge that slightly for you. When we're using the diagnose samples mode, the resulting image is a grayscale representation of sample density. So the black areas indicate no samples, while white areas indicate maximum samples as described in the render global's min and max sample levels. Now this red grid here is the task size or boundary size, and these are the tile sizes that the software uses to create the actual image, and this is by default set at 0 down here in memory and performance, which means that Mental Ray will come up with a task size that it deems appropriate for the resources at hand and the size of the scene. Typically that's 28 pixels, 32 pixels, somewhere in there in size, and that's what we see here. The next diagnostics mode that I want to show you here is the diagnose grid. It's found in this section in here. And this mode is used to depict X, Y, and Z axes with red, green, and blue lines in object, world, and camera orientations. This mode provides distance and size information between objects and is used for debugging. So let's do a software render with that enabled to world. We also have an option here for the width of the lines. We can adjust that in here. So I'm going to do a software render. And here we see, I'm going to maximize that image for you and dolly in. So here we see this red, green, and blue grid work, if you like, of lines. And it's used for scene debugging, for those problem scenes. The next diagnostics option we're going to look at is the diagnose photon option here. And this is used to optimize the number of photons being used. There's two modes, density and irradiance. Density and irradiance. And we also have a photon density field here. Right now it's grayed out. If we turn it to density, that field becomes enabled. The photon density is the averaging of red, green, and blue irradiance components, and the photon irradiance is the total incoming illumination. So let's just do a software render here with this turned on, and we're going to change the photon density from 0 to 100. And let's go over here and do a software render. So let's have a look at these colors here. Just maximize that image and dolly in slightly. And I'm just going to close down render globals so we can have a good look at this. So once rendered, areas that are blue indicate no photon density at all, which makes sense because what we're looking at right now is the caustics that are being generated by the glass sphere in the scene. Areas that are red indicate photon density values entered, and by that we mean, let's open up render globals again, this value in here, 100. So the range in color values in increasing order of photon density is blue for none, cyan, green, yellow, red, and finally white. So let's just dolly into this section in here, and we see blue, cyan, green, yellow, and red, and then finally white over in this section in here, meaning that the number of photons in that area is exceeding the caustic accuracy statement in here. The last mode is the diagnose BSP mode. This mode gives a visual of the BSP, or binary space partition tree. Basically, the BSP acceleration algorithm breaks down scene geometry into an organized structure of recursively arranged voxels or volume elements. Now these voxels are placed by the algorithm into a nested or recursive pattern. From a conceptual standpoint, this recursive structure resembles a tree with a main trunk, the initial voxel, and then the many branches as the geometry is recursively placed into the voxels. Now there's two modes of operation. There's the depth and the size. Let's do a software render with the depth option enabled. And going to maximize that image and dolly in again. And what's happening here is that the blue areas indicate a very low recursion level in the BSP tree, And the color range goes through cyan, green, yellow, and finally red. And we don't see any red in this scene, and that indicates that the maximum BSP depth here hasn't been attained in the recursion of the geometry in this scene. So if we had reached a recursion level of 40, we'd start seeing some red areas here where the geometry count is very high. The mental ray for Maya map visualizer is a useful visual cue for understanding and refining the output of global illumination photon mapping as well as final gather. The information is available to users interactively in a camera or perspective window. Prior to mental ray for Maya version 6, the visual feedback would have been done for photon mapping using the Render Global's diagnostics functionality, and in the case of a final gather, you'd have to use the mental ray standalone application. So the visual feedback from the map visualizer can be quickly identified and understood using the map visualizer. The results can be used for faster tuning and more efficient rendering. So let's just make sure we've got final gather turned on. We do just 100 final gather rays. And we can scroll down to the Enable Map Visualizer section and enable that and do a software render. And we'll see over here in the interactive, in the perspective window, I'm going to maximize that window and dolly around. You see a very fine network of red dots here. We're going to just adjust the size of those dots or sample points that are used for the final gather calculation. Go to Window, Rendering Editors, Mental Ray, Map Visualizer, and we can increase the point size here so that we can more clearly see the final gather sample points as well as the normal scale. So it's quite interesting to note that this section behind the sphere doesn't have any sample points from our render, and that the sample points increase in intensity in this section over here.